Good morning, everyone. I'm Jeong from SK hynix. Today, I present our work on joint UFS for smartphone. This is a joint work with SK hynix, Google, and Seoul National University. We explore a simple question. Can joint storage work on real mobile device? Our answer is yes. It works, but it requires careful cross-layer design. Smartphones are now the dominant computing platform. User experience only depends on storage performance. Applications are large, background services are persistent, data keeps growing. So storage stability is not optional anymore. It directly affects responsiveness. If storage latency spikes, users feel it immediately. So, let's first look at today's mobile storage system. UFS is the standard storage interface in smartphones. UFS delivers high bandwidth under strict power limits. It works well today. But one structural issue remains. As capacity increases, mapping overhead increases. But internal SRAM does not scale. This mismatch becomes bottleneck. This mismatch becomes a serious issue when you get address mapping. Flash storage can't overwrite data in place. Because of this, the storage device must translate logical address to physical locations. Page-level mapping offers high flexibility, but it requires a large mapping table. In mobile devices, where the SRAM is very limited, maintaining this mapping becomes a serious bottleneck. For example, for a 1 terabyte UFS device with 4 kilobyte logical pages, the first level mapping requires 1 megabyte of storage. So, this structure requires many mapping entries, which is hard to manage with limited SRAM. And fragmentation is common in real devices. To understand this, we analyze storage fragmentation in 10,000 real smartphones. After about 1 year of use, we define fragmentation based on the ratio of 30 segments. About 30% of devices already experience fragmentation. As fragmentation increases, read and write latency increases significantly. This directly impacts performance stability. To address this, we explore ZUFS. ZUFS divides storage in zones. Write must be sequential within each zone. Instead of page-level mapping, we use zone-level mapping. For 1 terabyte capacity, about 1 gigabyte in UFS, about 8 kilobytes in UFS. The entire map fits in SRAM. Also, device-level ZUFS is removed. ZUFS becomes host-managed, but integrating this into Android is not simple. This slide shows how joint UFS is integrated in the Android storage stack. UFS semantics are not handled by a single layer. They must be enforced end-to-end from the file system through the block layer down to UFS devices. This requires cross-layer coordination. During deployment, we faced 3 challenges. Based on these observations, our goal is to make UFS work reliably in mobile systems. To achieve this, we focus on 3 key issues. First, multiple open zones increase write buffer pressure. Second, mobile power management can slightly break write ordering. Third, large zone increase garbage collection cost. Foreground ZUFS directly hurts user responsiveness. These challenges show that UFS does not naturally fit mobile system without careful cross-layer design. So we design coordinated end-to-end solutions. First of all, this is the overall architecture of GFS. The device is composed of multiple TSC NAND dies. It's organized into 4 planes of blocks and pages. Each page has a size of 60 kilobytes. ZUFS logically aggregates blocks across die and their planes to form zones. In our device, the zone size of 1056 megabytes. This configuration aligns the zone size with the physical superblock. First, write buffers. In UFS, multiple zones must remain open and each zone generates its own write stream. With static or host-managed buffering, limited SRAM leads to buffer thrashing. To solve this, we design Coded Zone Aware Buffer Management, GABM. This is a device-side scheme. It dynamically allocates and shares buffer across zones. This allows the device to efficiently support multiple open zones without any host-side modification. However, buffering alone is not enough. We also need strict write ordering. The second issue, write ordering, is not optional in GFS. It is a strict requirement. All writes within a zone must be issued and complete in order. For mobile system, can reorder writes due to aggressive power management mechanisms such as clock gating and I/O priority, FUA handling, EQ, scheduler behavior. To solve this, we fixed on UFS driver and block layer. In UFS driver, synchronized on gating waiting for clock for dispatch. In block layer, we set tracking pointer in re-enqueue events and route FUA write through serializing logic. Also, we impose zone ordering regardless of priority class. The third issue is garbage collection. In GFS, zones are large. So, each GC operation may migrate a large amount of data. Foreground GC directly delays user I/O. So, instead of waiting until space becomes critical, we triggered GC earlier. We moved more work to the background. This reduces foreground stores and improves response beneath. With these mechanisms, I now show our evaluation results. Our evaluation was conducted on a Google Pixel 10 Pro, which was released last August. The installed information is shown in the table below. For CUFS, we configure a conventional logical unit within the same GFS-capable device. I will start with random read performance, where GFS shows clear benefits. Sequential and random throughput is similar in current storage, but random read performance is critical for mobile user experience. This graph shows wide range random read performance on the fragmentation state storage. CUFS suffered from mapping cache misses, but GFS eliminates these misses. So, read latency becomes more stable and reproductive in wide range conditions. This slide isolates the impact of GABM. We compare sequential write through according to write buffer size for one zone. In contrast, GABM dynamically shares write buffers across active zones. As a result, sequential write performance remained stable even under limited buffers. This slide shows the impact of fragmentation on overall system performance. We made up fragmentation conditions and test based on them. the assumption of fragmentation conditions in which 4 GB was written with a small size and 2 GB was deleted. Module performance that write a new 1 GB file to measure write speed, then measure the peak read speed, and repeat it until free space remained 1 GB. In CUFS, higher fragmentation led to significantly higher and more unstable latency. This is mainly caused by frequency foreground GC and buffer contention. In GFS, maintains much more stable latency even under severe fragmentation. This stability comes from combination GABM with proactive GC. Also, this figure shows fragmentation behavior across iterations. As iterations increase, updates accumulate. In CUFS, pre-segments stably decrease while dirty segments increase. So, fragmentation level keeps rising. But in GFS, 3-stage GC reclaims space proactively. Pre-segments are restored early, so fragmentation does not keep growing. This shows that GFS actively controlled fragmentation growth through coordinated F2FS GC. Finally, we evaluate application level performance. We evaluate two scenarios, which is the issue of a large number of sequential and fragmented read requests. First, game loading time. GFS shows shorter loading time. Second, for loading scrolling, GFS shows low jank ratio. These results show that GFS improvements are visible at the application level. To conclude, this paper explores how GFS can be efficiently deployed in mobile storage system. We show that GFS significantly reduces mapping overhead by introducing a zone storage model that fits well within mobile constraints. Our results also highlight that fully realizing GFS benefits requires cross-layer optimizations, spanning the file system, block layer, and the UFS device. Finally, we open the door for further GFS usage and future improvement in mobile platforms. GFS works well on mobile devices, but we can see these benefits only with careful design across system layers. Thank you for attention.